297 winter quarter seminars, and some of you are new students here obviously in the seminar series. We have two of these for this quarter. The first one is going to be given by Professor Hess. Professor Hess has been at UC Davis since 1982. Actually, if this was an out-of-town meeting, technical meeting, he would not need any introduction, actually. But I know you are just students who are learning what is happening in the field. He is so well known in his field of human-machine interactions, flight dynamics, and automatic control of both fixed and rotary wing systems that he wouldn't need any introduction again. You will get to know him. I'm sure you'll take his graduate level classes from him. But today I want to give you a little more background about his accomplishments. He has obviously accomplished a lot, both in research and also from educational sense. He is actually one of the founder or accreditation of ABET accreditation of Aero program here at UC Davis. And he has contributed a lot, and he is recognized in many ways. He's a associate, he's a fellow of AIAA. He's also a senior member of IEEE, and he is the editor of many, associate editor of many journals. To give you a few names, one is he's associate editor of Journal of Aircraft of AIAA. He is also associate editor of IEEE Man Machine Systems. He is also in European Journal of Aerospace Engineering. So with that, please join me welcoming Professor Hess.
Thank you. Thanks, Nezrin. I think I'll just shut that down. Okay, this is going to be a little different talk maybe than you used to. There's some history here, kind of idiosyncratic. It's going to go fairly quickly through some topics relating to modeling the human pilot and why we might want to do that. We're now to over a century of pilot-vehicle interaction, okay? To begin with Orville Wright in 1903 in Kill Devil's Hill, North Carolina, the first powered flight. And you can jump forward to 2011. This is a young woman flying a Reaper aircraft. She is sitting at Creech Air Force Base in Nevada, and the aircraft is probably over Afghanistan. Okay, so this is the type of pilot-vehicle interaction that we're seeing. In a fine textbook written, I think first came out in 1967 by McCruer, Ashkenas, and Graham. Dwayne McCruer is a name you're going to hear quite often since he has been fundamental in a lot of this work in pilot modeling. The textbook is called Aircraft Dynamics and Automatic Control. This is a diagram that appeared in the text, and it was McCruer and Ashkenas and Graham's way to talk about the history of flight control development. Okay, it's a trident, and time is going in this direction. Okay, here you see that's the Wright brothers' first flight. There are three, as you might expect, a trident. There are three arms. The first one is called people dealing with the theory of aircraft dynamics. And these McCruer called these the scientists, theoreticians, and you'll see some famous names in there: Lanchester, Bryan, Williams, Bairstow, Melville Jones, Hunsaker, the first chairman of the Aero Department at MIT. In the second major element here, it's what McCruer called, this is automatic feedback control. It's what McCruer called the tinkerers and inventors. People like Hiram Maxim, the Sperry brothers developing their gyroscopes. Okay. Over here, again, the theory of feedback control, again, scientists, theoreticians. Again, famous names. If you're a controls type, you see Nyquist, Bodie, Harris. You see Evans, inventor of the root locus. The point is that these three elements, these three group of people, were not talking to each other. Okay, there were three separate elements until a marvelous lecture given in 1950 by Bollé. It was the 14th annual Wright Brothers lecture, William Bollé. Shortly after that, there was a series of reports funded by the Bureau of Aeronautics for the Navy called the Northrop Reports. Okay, the Bolle lecture is really an extraordinarily nice piece of work. It's 54 pages in length. I usually hand it out at the beginning of my graduate stability and control class. At that time, Bolle was at the University of California, Los Angeles. So, as I say, I do have a copy of it, and it is really a beautiful piece of work because he finally started integrating these three disparate areas of research. This is a Bode diagram taken out of the report of a open loop transmission, and I've emphasized something here that just beyond the region of open loop crossover, the thing has a slope of minus 20 dB per decade, and it's what he called the stable region. And we're going to come back to this time and time again in this talk. This is a prediction that Bolle made in the lecture, and here's what he said. He said, look, there appears to be no reason why a complete closed-loop stability analysis of the manually controlled airplane could not be made. Okay? The pilot would be represented by a servo system with particular reaction and time constants to signals such as changes in airspeed, normal and lateral acceleration. By making a reasonable representation of an average pilot, behaviors could be calculated and used to describe the flying qualities of the airplane. That was the first time this was said, and that really kind of sets the tone for the talk, because that is indeed what occurred as time rolled on. The next document I talked about was a series of reports that was developed under sponsorship by the Navy Bureau of Aeronautics. The important one for us is one called The Human Pilot, and here it is right here. The purpose of this report, and it was written in 1954, was to kind of coalesce the research that had been developing in the waning years of World War II about modeling the human pilot as a control system element. Okay, and shortly after that report was written, the United States Air Force got into the act and again sponsored a study, and it was called the Dynamic Response of Human Operators. It was a Wright Air Development Report, 1957. Why did they do this? Well, it was sponsored essentially by two agencies at Wright-Patterson: the engineers at the Flight Control Laboratory and the psychologists at the Aeromedical Laboratory. The important thing is that they communicated in a common language. They really tried to talk to one another. They did not develop an arcane language only that the psychologists would understand, only that the engineers would understand. A little different than things are today. What did they do? They went back to some of the original, they reviewed, assessed, and summarized research by four important movers in the field. First one is Arnold Tustin, 44 to 47. That's not his birth and death. That's when he was doing work in pilot modeling, from Great Britain. This is the same Tustin, by the way, that you'll hear in a course in digital controls, developing the Tustin transformation. Lindsay Russell, based upon his MIT master's thesis in 51. Ezra Crendel, at that time with the Franklin Institute in 1952. And Jerry Elkind, at that time, was at the MIT Lincoln Lab in 56. Now, these are some of the early researchers who were looking at this idea of developing the human pilot transfer function. Okay. Let's look at Tustin's early work. He was trying to improve the performance of anti-aircraft gunners and also gunners looking at land targets. Okay, this was in the waning days. This is after World War II, but sometime during the war. And here's a cartoon of what you might think about what was going on. Here's a gunner, and there's the gun line of sight. He wants to be aiming at the target. Here's a reference line of sight. Maybe it's due north or something. There's a target heading, there's a gun heading, and there's an error. And the operator is turning this crank to reduce the error. That's a feedback system. Okay, there's a single loop feedback system, a human, and the gunner. And here are some of the early measurements of the gunner's transfer function and the combination, the loop transmission, of that transfer function times that transfer function. And this was a first, back in 1947. It looks like we could represent the human, well-trained, well-motivated human in a well-defined task as a transfer function. Okay. Now, if you go on a little bit, this is Lindsay Russell's master's thesis at MIT. The title of it was Characteristics of the Human as a Linear Servo Element, 1951. There he is there. He's got a little tracking wheel, and there's a display here with a vertical line that's moving left and right, and his job is to keep it centered with the control mechanism. Here are some of his measurements, okay, that he took. Okay, these are Bode diagrams of the transfer function. Here's Ezra Crendel's work. Things are getting a little fancier now. This was at the Franklin Institute in 1952. His work was called The Spectral Density Study of Tracking Performance, Part 1 and 2, Wright Air Development Center again. And here's a subject sitting in a cockpit trying to do some tracking on an oscilloscope screen. There is the computational network. Probably has a fraction of the computing power that my laptop does. But nonetheless, it was used to make measurements of the human transfer function. Here are some of Crendell's measurements. Here is the so-called loop transmission. It's the Bode diagram of the product of the operator's pilot's transfer function in the vehicle. And I can draw another line through there, and that line makes it has about a slope of minus 20 dB per decade. The phase is doing something strange. It's falling off rapidly here. You should see something at minus 90 degrees all the way. Well, the human operator has an inherent time delay. 300 milliseconds is about what you'll see, and what the effect that has on a Bode diagram is a constant phase roll-off. What's going on back here at low frequencies is the human is creating a type 2 system. Low frequency integration to zero out steady state errors. Okay, these now are the Bode plots, if you will, of just the pilot's transfer function. And they look almost like pure gains, again with some roll-off. These measurements are pretty crude, but you got to remember that things weren't, the measurement capabilities weren't all that great at that time. Jerry Elkind's work when he was at Lincoln Lab, characteristics of simple manual control systems. Okay, these are again Bode diagrams of the operator's transfer functions combined with that of the vehicle. Okay. How do you make these measurements? Well, it's quite simple. Again, here's McCruer's name appearing, Dunstan Graham, and Duane McCruer. It's a very fine textbook called Analysis of Nonlinear Control Systems, first published in Princeton University Press. Here's a task. We've got a controlled element. We've got a pilot. I can measure the pilot's transfer function as a ratio of cross-power spectral densities. Take the cross-power spectral density between input C and the operator's output delta, divided by the cross-power spectral density between error and the input. That gives me an estimate of YP. You can do this in various ways. I'll make these measurements. I have this signal in here, and it's called the remnant. It's part of the pilot's output that cannot be linearly correlated with the input. You might call it noise. Well, you can measure the power spectral density of the noise using measures like this. Well, this is what these guys were doing. And as time went on, the measurements got more and more accurate. What McCruer and Crendell concluded from this study, from this report, is that on the basis of the correlations and explanation, it definitely appears possible to define mathematically, within limits, the dynamic behavior of the operator, parenthesis pilot, for the class of tasks considered. Okay, so they're starting to nail this stuff down. It's somewhat interesting in this era when you see, centers of excellence with budgets in the millions and the casts of thousands. You got these 4 people, 5 or 6, who are doing this fundamental research and really making an impact. And it's maybe an indication of a time lost long gone. The quality of the work was called out nicely in a book called The Body in Question. This is Jonathan Miller, Sir Jonathan Miller, by the way. He's a Cambridge-trained medical doctor. He's best known for example, by directing theater and opera. He's a real polymath. He got his first start in theater by being part of a group that's called Beyond the Fringe. Maybe some of the old-timers can remember that. It was a British comedy review, and he worked with such notables as Peter Cook and Dudley Moore. But it's an interesting book, and it began as a 13-part BBC series on the history of medicine, and then it was published on PBS in America. Well, here's what he said. It's a very readable document about human physiology, and here's what he had to say about this work that was going on. They, being those researchers, realized that they had created a revolutionary model for thinking about muscular performance in general, and that the tracking tasks which they had analyzed were examples of what the nervous system was called upon to do throughout its life. And then he went on to say, it is no exaggeration that the collective experience of the human operator in control systems laid the foundations for not only all neurophysiology in the late 20th century, but created the science of cybernetics. All due apologies to Norbert Wiener. That's pretty heady statement to make. Anyway, The Body in Question, 1978. Now, After that report, there was more interest by the Air Force primarily in continuing the study. In particular, how does the pilot's transfer function relate to how difficult he views the aircraft to fly? So here's some, again, Bode plots, just the magnitude plots. And what they were doing was taking the short period dynamics of an aircraft and varying the undamped natural frequency and the damping ratio of the short period mode, put the pilot in a very simple simulator, fly it, ask him what does he think of it, how difficult it was. If the pilot acts like a pure gain, that is, his Bode plot is, this is just the pilot now, his Bode plot amplitude is flat, he said, that's good. If things start to occur where he has to generate lead, he puts a 0 in his transfer function out here, he said, it's acceptable. If things get worse and the 0 that he has to put in comes down to lower frequency, he said it's poor. And if the 0 is far down at low frequency, he says this is unacceptable. Okay. So increasing pilot lead generation, the pilot literally putting a 0 in his or her transfer function leads to a deterioration in performance and in acceptability of the system. Okay. All right, that was the first time this had been shown. There's the document, again, McCruer, Ashkenazi, and Gare, a systems analysis view of longitudinal handling qualities, right air development once again. Okay, it goes on. The Air Force says this is looking good. We want to keep doing this. And this is a document which is a classic. It's called Human Pilot Dynamics in Compensatory Systems. People who work in the area just refer to it as 6515, Air Force Flight Dynamics Laboratory. Very well-controlled experiment, single axis. Now we're getting some high-quality measurements. This is the loop transmission, the product of the pilot's transfer function in the vehicle. In this case, I think it's just the pilot. No, it is. It's the combination of the two. And also there is a remnant power spectral density over here. The combination of these two you call the describing function. Okay, so things are getting a high quality now as far as the measurements go. All right, here's a perfect example of the pilot adapting to different vehicle dynamics. Single axis task. There's the vehicle, there's the pilot, there's some external command coming in, some response. The error signal is right here. It would be displayed on an oscilloscope screen. Here's what happens when the controlled element is a pure gain. I see minus 20 dB per decade. That's the combination of the pilot and the vehicle. Here's what happens when the controlled element is a velocity system, K over S, minus 20 dB per decade. Here's what happens when the controlled element is K over S squared, an acceleration system, minus 20 dB per decade. Some strange things appear to be happening with the phase. The high frequency roll-off is due to the time delay. The low frequency roll-off is due to the fact that the slope up here is minus 40 dB per decade. The pilot has put two poles at the origin. Okay? What does that mean? Type 2 system, 0 steady state error to a step input, 0 steady state error to a ramp input, constant error to a parabolic input. Okay? All right, and by the way, this is called the crossover model. Around the open loop crossover frequency, where the amplitude portion goes through 0 dB, the transfer function of the pilot times the vehicle will look like omega c over s with a time delay. And sometimes called McCruer's law because he was really the guy that teased this out of all this data. This is some work, believe it or not, back in 1965. I was a junior at the University of Cincinnati, and we had to write a bachelor's thesis. I was a cooperative engineering student at Wright-Patterson, and it was an exciting place to be because all these guys doing this fundamental work were coming through there. Okay, they were sponsored by the Air Force. And my thesis was called The Human Operator as an Element in a Control System with Time-Varying Dynamics. This is the experimental setup that I had. This is the largest analog computer in the world at the time. This is only a little bit of it. It covered a whole room about the size of this, and we just had one little corner. And this is my test subject. This was a senior. I was just a junior, Gene Fleeman, and he agreed to be my subject. And it was interesting work. And Gene went on to some fame for himself because he's the author of one of the definitive texts on tactical missile design, and it's published by the AIAA. So anyway, I got in this in 65 when I was just a BS student. Again, I was co-oping at Wright-Patterson Air Force Base. Okay. If you ask a seasoned control system designer, what would you do if this was the controlled element and this was a compensator that you had to design? to give good performance and stability, he would probably say, I'm going to use the primary rule of thumb of frequency domain synthesis. This is not talking about a human in there, inanimate controller. What does that rule say? Find or create a fair stretch of minus 20 dB per decade slope for the amplitude ratio of the loop transmission. Make it the crossover frequency by adjusting the gain so the 0 dB line goes through it. Choose the crossover frequency as the desired closed loop bandwidth. Make sure that at low frequencies the loop transmission is big, and at high frequencies it's little. So the human operator, the human pilot, is adopting, creating his own or her own transfer function that obeys that law. The same thing that a designer would do for an inanimate control system. So there it is. There's the open loop Bodie diagram. You do see this phase roll off here. This is the same thing on a Nichols chart. Okay, so that's kind of interesting. It was a nice interplay at that time to see that what the human is doing is the same thing that a control system designer would do, given the choice of zeros and poles in a compensator. Okay, as the ability to measure human pilot dynamics proceeded, there was an increased interest in what are called modeling the neuromuscular dynamics of the pilot. The dynamics of the human arm if it's a control stick, or the legs if it's a pedal system. And you can begin to see that now. This is just a Bodie diagram of a single pilot's transfer function. And you begin to see this peaking out here. And that peaking is part of this neuromuscular mode. Okay? And this became important as they were interested in designing manipulators for high-performance aircraft in the cockpits. Okay, let me just a second and step back and say everything I've shown you so far has been guys sitting in an air-conditioned laboratory, nice and quiet, tracking a line on an oscilloscope screen. What happens if you do the same thing in an airplane? Well, the first time this happened measurement was in 1968. The paper was written by Fred Newell of Calspan, that was Cornell Aeronautical Laboratories, and Paul Petchock, who was at the Wright-Patterson. The airplane was the Calspan NT-33. It's a variable stability aircraft. There is a computer on board that can make the aircraft fly like a variety of other aircraft. Okay, it's interesting. Richard Hallion, I heard him speak a number of years ago. The curator of the National Air and Space Museum said, "This is the most successful research aircraft that's ever been built." And there's a lot of competition in there. It looks rather mundane, but it's now sitting at the museum in Wright-Patterson. Okay, so here are measurements in flight. This is just the Bodie diagram of the pilot's transfer function for a world tracking task. They had a head-up display in the cockpit, and an artificial horizon was moving, and the pilot was attempting to track it laterally. They measured his transfer function using the same ratio of power spectral densities that I showed you before. It's interesting. This is a real airplane. Okay. Here is some work. This is a space ed, so I better bring in a spacecraft. This is a paper written by two former colleagues of mine back at NASA, the late Rod Wingrove and Fred Edwards, called Some Examples of Pilot Vehicle Dynamics Identified from Flight Tests, published in the IEEE Transactions on Man-Machine Systems. This is John Young and Michael Collins in Gemini 10, and what they were doing, they were controlling the yaw motion of Gemini 10 in retrofire. And what Rod and Fred did was to measure the pilot vehicle dynamics again. What do you see? Minus 20 dB per decade, high frequency phase rule off due to time delays. Okay. In 1986, one of my grad students, Mark Minnick, got a grant to go down to NASA Dryden and participate in some flight research. And this was interesting. We had a real honest-to-God F-14 chasing a real honest-to-God T-38 over the desert down there. And the task, it's a little hard to see. It was two things. A tail chase in which the F-14 was 800 feet behind a T-38, and a 3G wind-up turn, tried to maintain 800 feet separation again. What was the task? Well, the F-14 had a little reticle on the head-up display, and it was driven automatically, vertically, by a sum of sine waves that looked random to the pilot. The pilot's job was to keep that reticle on the tailpipes of the T-38. Okay? And so Mark went ahead and measured the pilot vehicle dynamics in the wind-up turn and level flight. There are the results with two measurement techniques, fast Fourier transform, and another one using output error estimation. 20 dB per decade, 20 dB per decade. Okay? We noticed on this, by the way, that the crossover frequency for the level flight was considerably lower than the crossover frequency of the wind-up turn. That means this was being flown more aggressively, and we couldn't figure out why. We said, oh, something's wrong with the measurements. We did something wrong. So as a final a final task, we asked the pilot. And he said, well, look, when I'm behind the T-38, I'm getting bumped around by the wake from the airplane. And it doesn't do me any good to try to track better. I'm just getting bumped around. When I do the 3G turn, the wake is getting blown by me. It's very nice, steady air, so I can track more aggressively. And that's what you're seeing here. Okay, a higher crossover frequency means a higher closed-loop bandwidth. Okay, some more in-flight validation done here with the CalSpan NT33. More interest in what's going on with this peaking due to the neuromuscular dynamics in combination with the manipulator. It seems like a lot of effort just to worry about what's going on with the control stick. But around this time, some nasty oscillations were occurring in high-performance aircraft. It's called roll ratchet. When pilots were doing a very rapid snap roll, the aircraft would get into a high-frequency oscillation. And it wasn't loss of control, but the pilot's head was getting whapped around, hitting the side of the cockpit, and they couldn't stop it. And they found out that it was due to what we call biodynamic feedback. When you do a snap roll, your hand wants to stay the same place in inertial space. It rolls the stick over, so you start to roll to the right. The airplane snaps over, but your hand pulls the stick back. Okay, and so this causes an oscillation due to its interaction with the stick. So there's a lot of work done on the effects of cockpit lateral stick characteristics on handling qualities. There's different. The reason there are different peaking going on here is because there are different control sticks in there. Okay. More neuromuscular dynamics. McCruer et al., Dwayne McCruer, Ray Magdaleno, and George Moore, who was on the faculty at UCLA, published this paper on developing a model of the neuromuscular dynamics of the pilot. Things are getting fancy now. There are some inner loops being closed. The muscle spindle is a receptor in your muscles, and there are lots of them, and what it measures is muscle length. Okay, and it provides an immediate signal to the central nervous system that that muscle is being extended, provides some feedback to stop it. This is a joint angle receptor. There's a marvelous system. These are called proprioceptors. I can put my hand behind my back and I know exactly what's going on. I can't see it. I don't feel any accelerations. The proprioceptors are giving me that information. The spindle, by the way, is why when the doctor, you go in for your medical examination, sit on the table, the doctor hits your patella, and your knee and your leg pops up. The muscle spindles have felt that that muscle has been stretched, and they bring the leg up to reduce the stretch so as not to harm the muscle. So anyway, things are getting fairly fancy now. These are a number of types of control sticks, so-called force and free-moving manipulators. Okay, let's go back to this idea of lead generation and the pilot putting a 0 in his or her numerator. This is the Cooper-Harper pilot rating scale. Test pilots use this scale to quantify the handling qualities of particular aircraft in particular tasks. Its scale goes from 1 to 10. 1 is optimum, 10 is uncontrollable. And the scale is broken up into 3 levels. Level 1 is desired, level 2 is acceptable, level 3 is forget about it. You got to fix it. Okay. Here's a pilot transfer function, and what the guys, again, McCruer and company did is they took a bunch of tasks in which they knew the pilot's lead time constant would have to change. And then they asked him to rate the task. And sure enough, as the lead time constant went up, as that 0 went down to lower and lower frequencies, the ratings deteriorated. You got a rating decrement of 3 on a Cooper-Harper scale. Once again, lead is bad. If the control element that you're flying, if the aircraft that you're flying has dynamics that require lead, the pilot will downgrade it, performance will be degraded. We're going to return to this and we're going to talk about an accident a little later on. So some of the work I've been doing now is using pilot models to analyze and design control systems. And what should a real pilot model be able to do? Well, it should be able to provide predictions of task performance that an actual pilot would generate in a given task with a given airplane. It should be able to simulate varying levels of visual cue quality, varying levels of pilot aggression. How hard is the pilot working? Provide estimates of handling qualities, and the last one is be reasonably tractable. That is, an analyst can actually use it. Okay, one of the models I've developed and been using for a long time, this first came out in '97, was something called a structural pilot model. Output here might be the pitch attitude of the aircraft. This might be some pitch attitude command. There are 3 feedback loops, a proprioceptive feedback loop, a vestibular feedback loop. That's where the pilot's inner ear sensors are working, the otoliths and the semicircular canals, and down here visual feedback. I found out by looking at a bunch of flight test data that came out of Cornell Aeronautical Labs that if I took the ratio of that signal to that signal, I called it the handling quality sensitivity function, divided it by that element, which is just a gain, I could make an estimate of where the handling qualities of the vehicle will reside by this chart. This is nothing more than the Bode diagram. That's linear frequency. That's linear amplitude. Normally a Bode plot is log frequency versus log amplitude. Well, all I can do, I would set up the model and I could plot this handling quality sensitivity function, and if everything stayed down here, the pilot would, I would predict the pilot would call it level 1. If it bumped up in here, it would be level 2, up here in level 3. Okay. Now, let's take an example of using this. Gianluca Cama was a student from the University of Brescia in Italy. He came here and worked with me for about 9 months working on his diploma in engineering. Essentially, it's like between a BS and an MS as far as a Europeans go. So we did this, and here's the paper, Flight Control System Design for Inherent Dynamic Damage Tolerance. It was published about 2 years ago in the Journal of Aircraft. Here's the airplane. We have a model of this airplane. This is the F-18. It's called the F-18 Harv. It was a NASA variant, high angle of attack research vehicle. It's got a lot of control surfaces on it. Leading edge flap, trailing edge flap, rudders, differential tail, thrust vectors, ailerons. In the model, we decided not to use the thrust vectoring. Now, a real honest-to-God F-18 does not have thrust vectoring. This one did. We then had data, and we're going to look at just lateral directional control. And we had data from 19 flight conditions, starting at Mach 0.6 at 5,000 feet, and all the way up here, Mach 0.9 at 40,000 feet. Okay, so we're going to design a control system, and then we're going to have a pilot model fly it, and have the pilot model tell us, good handling qualities, what's the performance? Okay. What are the requirements for the flight control design? Again, we're just looking at lateral directional control. We want to control roll rate with a lateral stick, side slip with the pedals. And what we said, the control design must accommodate all 19 flight conditions and maintain invariant control response characteristics over that entire envelope. Okay. We're going to introduce what we call effector actuator damage. We're going to screw up the model, and I'll tell you how we did in a minute. And we're going to do this with this pilot model flying it. Because we have said we don't want the control response characteristics to vary, we're not going to change the pilot model. We're going to design the pilot model for that low and slow case, and we're going to keep it constant all the way through. What we did then is we through computer simulation, looked at performance and handling qualities. Here's the control system design. It's using something called a sliding mode control system. Okay. Here's the control system block diagram. You got a bunch of effectors here. You've got aileron, horizontal, differential horizontal tail. You've got rudder, leading edge flap, trailing edge flap. And we only have 2 outputs that we're interested in, side slip and roll rate. So we create what's called a square control system. Okay, the number of outputs equals the number of commands. What happens, how do you get 2 into 5? You use what's called a control distribution matrix. You distribute those 2 controls to the effectors. There are many ways to do this. What we did, we used the same control distribution matrix that was used in an Air Force design, because we wanted to compare our performance to what the guys did at the Air Force Institute of Technology. Okay, so there it is. Turn the crank on the design, and here's the Bode diagram of the closed loop transfer rate. No pilots in here yet. This is just P, which is roll rate over the command coming from the pilot's stick. This is side slip coming from the side slip command coming from the pilot's pedals. That's a pretty good system. You got your flat out here. This is not the open loop now. This is the closed loop. You got a fair, nice bandwidth out there, and the roll control is above 10 radians per second. You get less with beta because it's just a little harder thing to control. Okay. We also stuck in this thing before the design a filter to preclude this roll ratchet stuff that I told you about earlier. This is a high bandwidth system. Okay, so that's what the pilot has to fly. So the next thing we do, we cranked up this pilot model, and we're going to say, look, pilot, keep your feet on the floor. Don't worry about side slip. Let the control system handle that. No beta tracking. We're going to give you a series of roll commands, the pilot model. Here is the open loop transmission with the pilot model in the vehicle, 20 dB per decade, 1.5 radian crossover frequency. Okay, so what we did then is say, what's the handling qualities at the nominal condition, low and slow. And what we found out was we're in level 2. What happened? What happened? Well, we decided we can fix that. That's what the whole purpose of this thing. So we took a little command filter that just operated on the pilot's output, control stick output. And we evaluated it again, and we got level 1. And there's a reason for doing this. It made the controlled element phi over phi command look more like K over S itself. Okay, so what do we do now? Let's start and evaluate it. Let's evaluate the handling qualities in the corners of this envelope. Low and slow, fast and low, high and fast. So I kind of run around there, and there are the handling qualities sensitivity functions saying, for a tracking task, he's going to get level 1 handling qualities. Okay, so let's see what happens next. We started screwing up the design as if we had damage. So what we did, we reduced the effectiveness of all the control effectors by 50%. Suddenly the aileron, maybe half the aileron's missing or something, and they're only 50% effective. We didn't do any aerodynamic modeling here. We just reduced the gain of the actuators. Okay, we added 50 milliseconds of time delay. That's always destabilizing. And finally, and this is kind of a biggie, we put a backlash element in the actuators, like they're worn. The actuators are suddenly getting sloppy. And what we did then was to give the pilot a series of roll commands, the pilot model. Here's the results, all 19 flight conditions. The command you can essentially see here, roll to 40 degrees, hold it for about 10 seconds, come back to minus 40 degrees, hold it for 10 seconds, and keep doing this. Right here is where we introduce the damage. And you can see there's some deterioration of tracking performance. But that's pretty good, given 19 configurations from low and slow to high and fast. This is the side slip variation. You'd like to see that right along 0. But we're getting a little bit. That's 10 times beta. That's a very small side slip. And the pilot's not doing anything, feet on the floor. So this is an example of why pilot models are useful. You can do a design, then you can do an evaluation, and then if you're confident in the design, you take it to pilot in the loop simulation or flight test. This is another student from University of Brescia. He came to work with me for about 6 to 9 months, again working on his diploma in engineering, Federico Marchesi. And we published this paper in the Journal of Guidance, Control, and Dynamics. And we were looking at flight simulator fidelity issues, but we chose a big whopping helicopter to do some pilot vehicle analysis. This is a CH-53. The Marines have this, and this thing could lift the building. You know, they're huge. And we looked at a couple tasks. We looked at XLD cell, and an XLD cell is a maneuver they use to evaluate helicopter handling qualities. I'm not going to talk about the second one here. An XLD cell, I got a little model. It sounds pretty mundane. You've got a helicopter and it's hovering, and you lower the nose and you go screaming up to about 100 knots, and as quickly as you can stop the velocity, come back to hover. It sounds boring, but if you ever see a large helicopter do it, it's frightening because the tail rotor comes very close to hitting the ground, and you see it. It's not unusual to see the vehicle come to 45 degrees. The interesting part is that a helicopter flying at 100 knots has a lot different dynamics than a helicopter that's hovering. So what we're going to do, we're going to come up with a time-varying pilot model. And there's what it looks like. Things are getting complicated now. It's not just one axis. The pilot is controlling pitch, roll, yaw, and vertical velocity, and then some outer loops around that, controlling position. Okay, that's a Simulink diagram of the pilot vehicle model. Here is a typical simulation result. This is the blue line here is velocity. Starts here, gets up to 180 feet per second. That's 100 knots, and then takes it out here. Here, this is the pitch attitude. You see the nose coming down, speeding up, the nose comes up, and you stop. There's a little variation in roll, because these vehicles are dynamically coupled. But nonetheless, we have a time-varying vehicle model and a time-varying, I'm getting very good going here, a pilot model. Okay. Aircraft handling qualities. There is something called pilot-induced oscillations that you may have heard of. It's a type of inadvertent, atypical, and unwanted coupling between the pilot's control inputs and the response variables of an aircraft. It's nasty. It's dangerous. The first one of those serious ones happened with the space shuttle. Fred Hayes was flying. Gordon Fullerton was second in command, and this was called Free Flight 5. And this is when they were doing some early testing, launching the shuttle off the back of a 747, coming and landing on the runway. The first 4 flights that were landing on the dry lake bed, you can go forever. Yeah. The 5th flight test, he said you got to land on a concrete runway at a specific point. And a pilot-induced oscillation occurred. It was pretty serious. Here's the pilot's pitch inputs. You see the oscillations going on. Here's the elevator response. Whenever you see straight lines in a angular response, that means the actuator is rate limited. That's bad news because it adds delays. Here's the pitch rate. The worst news was that they had a hard landing. You don't want to see first touchdown when you see this is altitude versus range, because it hit hard, bounced, hit again. NASA spent a lot of money and a lot of time fixing that problem. This led to the formation of a National Research Council study. I was honored to be a member of it, along with McClure and some other people. And it was worried about the possibility of these PIOs occurring in commercial fly-by-wire transports. Okay, and this is a book by Malcolm Abzug and Eugene Larrabee. Abzug is late of MIT. Okay, the book came out in 2002, and here's what they said. They said, look, based upon that NRC study, there's a potentially dangerous PIOs can occur in commercial aviation. These interactions in commercial transport airplanes have been covered, and a well-considered plan to stop these should be put into action. Okay, with that in the background, I was invited to a workshop at the University of Berlin, Technical University of Berlin, last summer, and it was on vortex encounters, wake vortex encounters. Any aircraft that's generating lift is going to generate vortices off of each wingtip, counterclockwise off the right wing, clockwise off the left wing, and these guys are powerful and they last a long time. Here's the group, here's yours truly here, and I gave a brief presentation, and one of the things I did was I took a model of a commercial aircraft for which I had data, and I said at the end of my talk, I have a significant concern that a vortex encounter can lead to a PIO, particularly if the pilot does the following. If he begins to coordinate pedal inputs with wheel inputs, left pedal, left wheel, right pedal, right wheel. It's a bad thing. And I've shown that in the paper I published in the Journal of Guidance and Control and Dynamics. It introduces significant lags in the effective vehicle dynamics. I took my seat. A guy sitting next to me from the University of Leicester in Britain said, have you seen this? And he slid his laptop over, and this is a... I'm going to skip that one just for right now. All right, the day before I presented my paper, a report came out from the Transportation Safety Board of Canada. That's an Air Canada A319. And what they said was, on 10 January 2008, an Airbus A319 was flying at 35,000 feet and 450 knots. It encountered the wake turbulence from a 747 that was 10 miles ahead of it. Okay, that's how these vortices stay. Okay. Well, what happened? Well, the Airbus captain reacted with combined lateral, stick, and rudder inputs. Bad. The rudder deflections exceeded plus or minus 5 degrees. Doesn't sound like much, but that's the rudder limit at that airspeed. The oscillatory event lasted 18 seconds. The frequency was about 2 radians per second. There were multiple passenger injuries. People getting thrown all around the cabin. So what he did to the passengers was nothing to what he did to the airframe, because the rudder input in response, the captain's response to what he thought was a control failure, he thought something broke on the airplane. Well, he caused the rear vertical stabilizer attachment to see 129% of its structural limit load, and the rear fuselage fitting to see 121% of its limit load. That's getting dangerous. You're near the point where you're going to twist the vertical tail off the airplane. And it came close to history repeating itself, because I was involved in a study with American Flight 587 in which the vertical stabilizer broke off the airplane. This is in Jamaica Bay, just outside of Kennedy Airport. The plane crashed, 265 people died, and the NTSB said PIO resulting from wake vortex encounter. Okay, so this is an example of this pilot modeling stuff, maybe now giving you some idea what to look out for. Okay, one other forensic study here. December 20th, 2008, 6:18 in the evening, Mountain Standard Time, Continental Airlines flight 1404, it's a Boeing 737, departed the left side of runway 34 right during takeoff. 37 injuries, no fatalities. The airplane never left the ground. Okay, here is the track. He's coming over here. This is kind of the temperature was about 24 degrees, so this is kind of a frozen field. Came across an access road here, came across an access road here, and came to rest here. You can see that they seriously degraded the resale value of the airplane. Okay. It's a miracle nobody was killed. It caught fire. I mean, it's got to be terrifying. You're taking off in an airplane. Well, you're not taking off. You're rolling down the runway. This started about 100 knots, and you start going off into the hinterlands in an airplane that's loaded to the gunnels with fuel. As soon as it got here, the whole entire starboard side of the airplane burst into flames, and luckily, the flight attendants were aided by 2 pilots who were deadheading. That means that there are two Continental pilots who are passengers are just getting a hop to their next assignment. They, in turn, in conjunction with the flight crew, kept everything calm. They got everybody out. More information about what happened. Here are the rudder inputs. Now, the question is, well, how does this happen? Healthy airplane. Yeah, it's night. Here's some, what happened was I was contacted by the NTSB and asked to provide a second opinion. I wasn't a major player in this. They said, well, what do you think of this? And so I gave them a report. I had a very short time frame to do it. Here are the pertinent takeoff conditions, and here's the troubling guy. The winds were from 270 to 290 degrees. And the runway is 34 right, so the winds are almost at 90 degrees. Okay, and they're gusting from 24. The crosswind was 24, gusting to 32 knots. That's a lot of crosswind. The pilots said they could see forever. It was dark, but they had these big taxi lights, and it was clear. It's 25 degrees centigrade, good visibility. The runway was dry and clear. Okay, so what's going on here? So I said, okay, let me take a look at it using a pilot model. But remember, this is not an airplane, it's a ground vehicle. So I did some real back of the envelope system identification, looked at a series of pulses that were going on with the rudder, matched them with the lateral acceleration, and came up with a model, the transfer function for the vehicle. Heading acceleration over pedal input, divided it by s squared to get heading over pilot input, and said, there's my system transfer function. This was the pilot's operating on. What do we got? 20 dB per decade. That's nice. That's what the pilot likes. But out here, about 0.5 radians per second, it starts rolling off, 40 dB per decade. What's that mean? The pilot has to generate lead to keep the airplane on the runway. And if he gets aggressive, he's going to get out here where he really has to generate lead. Bad handling qualities. Okay? So what I did is I set up my pilot model, and I played around with the crossover frequency of the gain. And I said, if the gain give me a crossover frequency of 1 radian per second, I get some oscillations. If I bump it up just to 1.3, I really start getting some oscillations in heading. And what made my day was that the oscillation frequency I was getting was 4.25 radians per second. And the NTSB said, hey, a sample of 10 of these aircraft in high crosswind takeoffs, the average interval between peak rudder inputs was 4.5 seconds. So it was a pretty close agreement there. I then took it a step further and set up a little simulation in my office. These are some rudder pedals. This is my laptop. I put the dynamics that I identified in there and put a very simple heading indicator. Generated some disturbances in crosswinds and said my job was to keep that guy heading north. And when I did that, I could generate some oscillations if I tried to get aggressive, 3.8 seconds from peak to peak. And if I went here, this is right from the NTSB, that's 3.8 seconds peak to peak in rudder. So I think that the pilot modeling experience provided some insight here. And there are some problems here other than just the lead generation. First of all, the rudder pedals themselves. You're controlling heading using the rudder pedals, which steers the main gear. Okay? And the rudder pedals, it takes on a 737 15 pounds to even get them to move, breakout force. It takes 70 pounds to make them go full force, full deflection. And the full deflection is only plus or minus 3 inches. It's not an ideal manipulator to do tracking in which you're trying to generate lead. The other problem is that the muscles that are running those guys are these guys. They're called the vastus lateralis, the most powerful muscles in the human body, and they're not good for precise tracking. But that's what the pilot had to do. So a whole bunch of conclusions here. Basically, the guy was really handed a difficult aircraft to fly. The crosswind gusting was right about at the limits for which the airplane is certified. The NTSB said, well, they need more training, and that's probably a good idea. Put the guys, when the guys come in for recurrency training, put them in the simulator and give them crosswinds of that nature. so they can become accustomed to the tracking. That's another thing I don't have time to talk about. There are some non-aircraft applications for this. This is not work I've done. This is a friend of mine, Randy Bailey, back at NASA Langley. They were looking at docking maneuvers for spacecraft, asking about spacecraft handling qualities. And this is the simulation they were doing in which you can use a pilot model. It's been what? 1990, one of my PhD students, Ali Mojahedson, and I developed a control theoretic model of the automobile driver, and we were able to match the driver responses very well with some data that was generated at the University of Toronto. Right now, with Jason Moore and Mont Hubbard and Luke Peterson, we're developing a model for the bicycle rider. All right. Turns out to be not an easy task to do, but we've got this early model. Here it is controlling bicycle roll. There are three loops: proprioceptive, vestibular, and visual. Here is the bicycle rider combination for heading. You see the crossover model in evidence. Here's a simulation task where we ask the guy to do a lane change maneuver. This isn't scaled funny. This is in meters here. It goes 1 to 3. 1 to -3. This is in meters here. It's 150. It's like putting a big painting a line on a blacktop parking lot and say, okay, go around there and follow yourself down. This is interesting. These are the steering inputs. By the way, the multiple colors here is 6 different bicycles Jason developed the dynamics for. You can see down here that something suspicious happens. When the guy goes to make a right turn, he steers left initially. That's what happens in a bike. You're going into a corner, you turn right, you're going to get a little reverse steering, and the bike is going to lean over to the right. It'll set you up for the right-hand turn. At the last Davis criterion, I put myself right on a corner behind the hay bales watching the guys come down D Street, take a sweeping left down 3rd, and you can see every one of them. There's a little twitch to the left. I'm sorry, this case a little twitch to the right. The bike leans over, they go around the corner. I was very happy that the model replicated that. Okay. We're done. I got to show one more slide here. Why do this? Why model the human pilot? Well, this is a quote from, again, McClure and Henry Jex. To summarize behavior, to provide a basis for rationalizing and understanding pilot control actions, and most important of all, to be used in conjunction with vehicle dynamics in performing predictions or explaining the behavior of the pilot vehicle system. Okay? Now, one other one, and I'm going to stop, I promise, is that everyone knows that automation is taking over, and the day is coming when there's not going to be a living pilot in the cockpit. And this is the robotic first officer talking to the robotic captain and said, you know, Captain, I haven't taken a day off in 5 years. Economics is going to force this. Okay? And the first airplanes that are going to use it are going to be freighters. The FedEx guys and the DHL guys are going to start flying transports without a pilot in the cockpit. Okay, that's it. Thank you.
Yes, thanks. We'll take a few questions.
I went long, I'm sorry.
Maybe 1 or 2 at least. Anyone has questions? Yes.
Usually we assume under normal conditions that the pilot will have a fair judgment of the conditions and he has a rational response. But in the abnormal conditions, his response may be unpredictable. So how do you account for that? The question actually is, when you switch from human pilot to automatic pilot and vice versa, you have to have both, actually. And then you have to make a decision of an independent system which say, this guy is crazy. You have to use the machine. Or the machine is broken. We have to use...
This is one of the big issues that researchers face. What's the role of automation? If you have a lot of automation, the pilots begin to lose their stick and rudder abilities. I was participated in a simulation study at NASA Langley. We were bringing in line pilots. We brought in a female first officer, American Airlines. She was flying Boeing 777s. She had the New York to Paris route. What is it, 6 hours? She says she flew the airplane at most 20 minutes. She was punching, altitude select, airspeed select, and it worried her because you start losing your stick and rudder capabilities. Another issue that's occurring is that they're developing adaptive flight control systems that can accommodate damage to the vehicle. The question is, something happens. The pilot's flying, something happens. The adaptive system starts changing. Is the pilot just going to be a benign participant in all that? or is he or she going to cause more problems? And this is a really active research area, as Mohammed indicated. That's kind of something I'm looking at now. When you have a pilot operating with a time-varying system, he may screw things up, or she, rather than help. I don't know if that's a good answer.
Yeah, I agree. One final question. I know you have. Okay.
Has the modeling of pilots ever gotten to the point of when pilot, when you have G loading and your blood all goes to your feet, and and blood pressure changing and all that? I mean, that's obviously way beyond.
Yeah, I mean, again, we're looking at a fairly benign task. We're not looking at loss of consciousness due to hypoxia or blood loss, or what you're talking, blood pressure loss. Now, there's been a lot of work done on alcohol and marijuana consumption on vehicle driving, and developing models to look at that. And basically what happens is the gain goes down and the time delay increases and the stability margins go away.
Okay, let's stop here. Thank you again.
You're welcome.